Computing. I am your instructor, Dr. Shubhadeep. Today is the last class of the current module. In the current module, we were trying to study the DRAM technology. Till now, we have done a deep dive and a detailed study on the fundamentals of the DRAM cell structure, both what it looks like in a textbook, just a 1T, 1C, and also what it looks in a fabricated chip. Also, the DRAM subsystem architecture, which was this inverted hierarchy of starting from the array, going up till bank, and then chip, then DIMM, and channel, and so on and so forth, which helped us gain a lot of parallelism and try to somehow mitigate the memory wall, which is the big difference in the performance of the CPU versus that of the main memory subsystem. Okay. Also, we looked in detail in the last one or two classes what are the mechanisms involved in the read and write and restore operation, and what is the importance of refresh operation. Okay. So today we will conclude our study of DRAM subsystem by looking at more technological aspects. We will see what are the challenges that are encountered when you try to scale the DRAM main memory subsystem. Okay, so we will list out what are the key challenges, and also we will discuss some of the solutions that have been implemented and are being proposed. Okay, so the first key issue that we are facing while trying to improve the performance of the DRAM subsystem. Remember, in DRAM subsystem, it was essential not just to get higher speed, but also higher bit density. So the problem that we are facing is that despite dimensional scaling, by dimensional scaling means you are able to indeed reduce the size, as you see in the x-axis is years, and in these circles you can see that the smallest feature size f is indeed reducing as the years pass by. But the problem is what is happening in the y-axis, which is your cell size. The cell size is saturating. So the saturating cell size, despite dimensional scaling, is a very big issue. And today we will discuss why that is happening. So first thing to notice is that in previous generations, lithographic alignment was a very big concern. But now with deep EUV lithography, that is also a concern, but that is not the real bottleneck. So what are the real bottlenecks? So the real bottlenecks is first and foremost maintaining the capacitance of the storage node comparable to the bit line. Remember why we had to do that? We saw the charge storage model. In the charge storage model, if the storage node is not comparable, the capacitance of the storage node is not comparable to that of the bit line, you will have big problems in getting sufficient noise margin. That is the first thing. The next issue is trying to manage the leakage in the access transistor. And that happens because when you scale down transistors, you suffer from short channel effects. And if you cannot manage leakage in the transistor, in the access transistor, the amount of time that you can allow for refresh, or the refresh rate, will keep increasing because charge will leak out much quicker. The other big problem is that of interconnects. Remember, DRAM is the first off-chip memory. So the reason for that is the capacitor that we fabricate in the DRAM chip cannot be integrated very easily with your logic operation or the CMOS advanced technology nodes. Therefore, you have to have two separate chips, and the communication between these two separate chips is fraught with large interconnect delay, lot of parasitics, which also will compromise on speed and increase power consumption. So because of these reasons, going to sub 10 nanometers of DRAM will become a very big challenge. Okay, so these are the roadblocks that are there in form of physical scaling of DRAM cell, and therefore increasing the bit density further of DRAM subsystem. However, there is another operational integrity challenge also, which I will just briefly mention. And the biggest operational integrity challenge is that as you reduce the dimensions of the cell, of an individual cell, and you pack in more and more cells into a small footprint, the distance between two cells will also start reducing. As distance between two cells start increasing, there is a lot of cross cell coupling or lot of cross cell interference effects. Okay, so there are several kinds of cross cell interference effects, but the one which creates a lot of havoc and which you will be able to appreciate more, I am trying to just give you an example. The example of something very interesting. It is called the row hammer effect. The row hammer effect. Now, this row hammer effect is a very serious challenge, and I will try to explain what this row hammer effect is. To explain the row hammer effect, what I have done is I have taken two DRAM cells which are very close to each other, and what is common about this DRAM cell is they have been connected to the same bit line. So two DRAM cells in a scaled architecture very close to each other, and they are connected by the same bit line. So what happens is, suppose this cell is what I want to write into. So this is the cell which I intend to write into. So how do you write into this cell? Of course, you will assert the word line to VPP, or VPP is your bootstrap voltage. Remember what is bootstrap voltage? Slightly more than your supply voltage, so that you can have lower parasitics and smaller read times on your DRAM or smaller read and write times, because you are reducing the parasitics of the access transistor. So what happens? You make this go to VPP and you are writing into this cell by making the bit line value to 0. Why? You want to write 0 onto this cell whose my intention is to write into this particular cell. However, what we see is that if we do this operation again and again, if we write into this cell, the intended cell again and again, the neighboring cell, which is also known as the victim cell, also develops a situation where the leakage on its storage node becomes very hastened. So basically, if we assume that on the neighboring victim cell we had a value of VDD on the storage node, it is seen that if you write into this neighboring cell again and again, it is seen that even the charge on the storage node gets leaked out much more faster. And as a result, if you can make sure that the leakage happens much faster than the refresh rate, what will essentially happen? You will be corrupting the data which is written in the victim cell. So why does this happen? Why is there a much faster leak? The answer is very simple. Remember, there will be cross coupling because these cells are very close to each other. So what is the first cross coupling? The first cross coupling that will happen will be at the bit line. So suppose these bit lines, because of them being very close to each other, will start cross talking with each other. This might be at you are not intending to write into this cell. So actually the value over here will be 0. But as you keep asserting the word line on the intended cell several times, it may so happen that there will be a finite coupling between the two word lines, and as a result, this transistor, which is normally should be off, will be getting slightly on. Okay, so slightly on means also the leakage will be faster. Not just cross coupling between the word line. Please recall, the bit line between them is also common. If the bit line is common and this is on, and instead of making it VDD by 2, which is your natural state, if you keep making the bit line 0, the leakage will even further get hastened. Why will the leakage get hastened in this case? Because this is VDD, this is slightly on because of cross coupling, and this is also 0 instead of being VDD by 2. And this is a very, very big threat. And often these hackers, what they do is they again and again try to write into a cell so that they can corrupt the neighboring cells. And this is a big hardware security threat. And how companies are trying to mitigate is by not giving visibility to the end user on which row or column you are writing into. So there is some kind of internal encryption or scrambling happening. So I leave the topic at that. It's a very vast topic and you can do a little bit of reading on yourself. Okay. Now that we have discussed what are the main DRAM scaling challenges, we will start looking for solutions. Remember, the main problem, the key problem was trying to maintain respectable value of capacitance, which is compared to the bitline capacitance. We have been looking at the shared capacitor charge capacitance model for DRAM in detail. So I will not again go to the, again repeat it. Remember, the change in the bitline value was VDD by 2 multiplied by the charge sharing ratio. Okay, the charge sharing ratio ensured, mandated that if the value of capacitance of bitline is around in the order of femtofarads, at least the value of the CSN or the storage node capacitance should be in the order of 40 to 100 femtofarads. Why is that the case? If the value is much lower than 40 to 100 femtofarads, the delta VBL that your sense amplifier will see will be very, very less, and therefore your sense margins will go for a toss. Okay. So the natural question then which comes to our mind is, in our regular CMOS processing, you have your gate oxide, which is a very thin gate oxide, and therefore it is supposed to have very high capacitance. Remember, C is inversely proportional to Tox. So why can't you use the CMOS gate capacitance itself for making this storage node capacitor, and why do you need to go to really complicated designs? And the answer lies in doing some very basic math. So let us do the math. What I have tried to find out is what is the effective gate capacitance, not normalized gate capacitance, but not the effective gate capacitance, but the net gate capacitance of a transistor oxide in the 14 nanometer FinFET node. So I have just put some numbers. Don't worry too much about the numbers. Area I have taken to be 50 cross 50 nanometer square, epsilon R to be that of SiO2 of 4, Tox of 5 nanometers. So don't worry too much about the correctness of the numbers. I'm just dealing with orders of magnitude. And when you put in these numbers, you see that actually the oxide capacitance that is offered to in a advanced technology node like 14 nanometer node is just 17 attofarad. What is atto? Atto is 10 to the power of minus 18. What did we require? We required almost 0.1 picofarad, which is 10 to the power of minus 14. So 10 to the power of minus 14 is what we needed. What we get just from CMOS gate oxide is 10 to the power of minus 18. So there is a big gap, around 4 to 5 orders of magnitude of what CMOS process can offer as a gate oxide and what we really need in your DRAM capacitor. So what is the solution? One strategy is very simple. Let's look at this equation very carefully. Either you try to increase your epsilon R, because epsilon 0 is permittivity of free space, that's a constant. Either you increase epsilon R from SiO2 to TiO2, zirconium, hafnium and your high K dielectrics, and you reduce Tox also from 5 nanometer to 2 nanometer or whatever it is. This will have its own set of problems. Remember, if you reduce Tox too little, it may so happen that your gate leakage starts increasing, and that will affect your refresh rate also. But be that as it may, you have to understand that even if you increase the the epsilon R value to some extent, reduce the Tox, it will only help you partly. It might help you 1 order of magnitude, half a order of magnitude, or maybe maximum 2 orders of magnitude. But we are off by several orders of magnitude from our target storage node capacitance. The solution lies only in playing with area. How can you increase the area of your storage node capacitance? And the only way to do that is by having high aspect ratio structures. So this is a high aspect ratio structure, and the first technology to develop these high aspect ratio structures was called the trench capacitor. We'll soon discuss why it is called trench capacitor. Just a very interesting note, developing high aspect ratio structures is for higher effective area is actually inspired from biology. Let me give you a hint. You see your wall lizard being able to maintain its weight, be able to counteract its weight while climbing on the lizard, climbing on the wall. Or basically, how does Spider-Man be able to climb on these walls? Or how does a lizard be able to climb on these walls? Actually, what happens is at the feet of these lizards, there are these similar high aspect ratio structures which increase the net surface area, which increase the van der Waal interaction between their feet and the wall, and that's why they were able to counteract their body weight. So all of this is actually the main inspiration is coming from biology. But how is it done in semiconductor systems is what we will see. So how you develop the trench capacitor is first you start with bare silicon and then a trench is dug. So this hole is dug. This huge hole is dug using one of the advanced technology processes such as deep reactive ion etching. Okay. After you do that, what you do is you then deposit the dielectric material. Let me indicate the dielectric material. So dielectric material over here is indicated in this white color. So this dielectric material generally is hafnium oxide, zirconia, titania, so on and so forth. Okay. Sometimes you use several layers of these dielectric materials also so that you can reduce the leakage through the storage node capacitor. Once you do that, the rest, what you see is then covered. The trench is next filled with your inner electrode. So you see this is your inner electrode. This inner electrode consists of heavily doped polysilicon. So finally, this becomes your one terminal of your capacitor, and this common substrate, P plus dope substrate, becomes your other capacitor terminal. Now remember, the substrate plate we have seen previously also was common across different cells in the same substrate. Okay, so this is how you fabricate your storage node capacitor using the deep reactive ion process. Next, only after you have done your processing or fabrication of your trench capacitor, you move on to fabricate your access transistor. The access transistor shares a common terminal with the inner electrode of your trench capacitor, right? And the other electrode or the other source or drain terminal is connected to the bit line. Of course, as you know, the word line is connected to the gate of the transistor, and this word line is what dictates whether this transistor is turned on or off. Okay, so this is what is in nutshell the fabrication of the trench capacitor. Now the trench capacitor has made lot of significant advances, and this is a image I have taken from the Infineon press release. It is a cross-sectional transmission electron microscope of one of these trench capacitors, and see how wonderful, beautiful structures they have been able to make. These are your cells or your cell transistor or access transistor right at the top. The aspect ratio of the storage node capacitor, which is constructed by digging trenches inside silicon, the aspect ratio is roughly 75:1. Now, there are several, this is a very wonderful technology, but there are several challenges also with scaling the trench capacitor model. First is that, remember, the feature size is 8f squared, or the normalized feature size for the trench capacitor technology is 8f squared. It is not 6f squared. Why is it 8f squared? Because the trench capacitor is slightly offsetted with the access transistor. Not only that, there will also be a locus or shallow trench isolation to isolate this particular cell from its neighboring cell. So you have to maintain some space because you have to accommodate the trench capacitor also, and you have to give some margin for making sure or isolation, so that there is very less cross coupling between neighboring cells. And this is why there is a prohibitive 8f squared scaling rule, which is only possible when you come to this technology of trench capacitor, right? Moreover, what happens is there are some fabrication issues which also come to the fore, such as when you start increasing the aspect ratio of the deep trench, it becomes very difficult to do a conformal deposition. Conformal means uniform deposition throughout the trench. Doing this uniform deposition throughout the trench becomes very difficult with atomic layer deposition. Okay, so and this increases the resistance of the trench fill. So to move away from this technology, people started developing something called the stacked capacitor model. So in the stacked capacitor model, the best way to understand is the trench capacitor was more like basement parking, right? So you have your house, and slightly shifted to it is your basement parking, where you have to go underground and park your car. Whereas your stacked capacitor model is you park your car above on the roof of your head. So in this case, you remember in the previous slide we saw this was the cell access transistor and your trench capacitor was somewhere over here. Okay, but in your stacked capacitor, the capacitor is actually on top of your access transistor. Okay, and in 2000s or early 2000s, the DRAM industry switched exclusively from trench capacitor to stacked capacitor model because it helps you in reducing dimensions from 8f squared to 6f squared. So you go from the basement model to the skyscraper model. So this is the image of a stacked capacitor model coming from Samsung. So this is Samsung's technology node. I think this is the 22 nanometer Samsung technology node, where you can see the capacitor stacks of DRAM. This is your common bit line, and these are your word lines for your cell transistor which are going through. So the bit line is in the plane of the paper or the slide, and your bit line is going into the plane of your slide. Okay, so the good thing about the stacked capacitor model was that you were able to scale from 8f squared to 6f squared, and there is also promise for better aspect ratio. There is promise that you can make the size of the cell capacitors, or the aspect ratio of the cell capacitors, even more steeper than 75:1, the record that we saw in the previous slide with trench capacitors. However, there are also some difficulties. The difficulty is that metal routing at back end of the line becomes very difficult. What is the meaning of metal routing? Remember, these transistors which are fabricated at front end of the line have to be connected with each other through metal layers. You have metal layer 1, 2, 3 and so on and so forth. So, but in that place, if you put this capacitor stack, then metal routing becomes a big issue. Okay, so this is why it becomes very difficult to use them for embedded DRAM applications, something that we will discuss very soon. In the one thing that I want to mention before we move on to our next topic is that all of these advancements in DRAM technology was only possible because there was a parallel lot of effort which was put in having giant leaps in your nanofabrication technology, and that has what has really enabled DRAM scaling. So I just want to quickly mention what are these advancements. One is your deep EUV lithography, which allows you to print very small dimensions. Then you have your deep reactive ion etching, which can create this really wonderful aspect ratio of 1:100, now even 1:200. The next is atomic layer deposition. The conformal coating of these trenches or the stacked capacitor is very essential. Just imagine you have a very thin surface and you want to conformally coat or uniformly coat this substrate. This was only possible through the development of high K or the deposition of high K dielectrics through this technique called atomic layer deposition. Okay, Without these giant leaps in nanofabrication technology, it is not possible to have these advances in the scaling the DRAM cell. Okay. Next, we move to a very important topic, which is trying to improve the performance of the access transistor. Now, we will see that the access transistor that we use is very different from your logic transistor. Why is this the case? We have already been able to scale the logic transistor to really small dimensions. So why do we need a different kind of access transistor? And to explain this, we will do a very simple calculation. What we are trying to see is how much should be the leakage current, the maximum allowable leakage current, so that you can meet the specification of having the refresh cycle every 64 milliseconds. The logic is very simple, that there is some charge that is leaking out of the storage node. That will be equal to CSN into delta VBL, as we have seen in the shared capacitor model. What should be the value of I leak for typical values of CSN, delta VBL and T reference of 64 milliseconds? And the number that we come up, I have put some values, the values are not that important, is that the typical values that your access transistors off current or leakage current should be is in the order of 30 femtoamps. Now 30 femtoamps is very, very, very tiny amount of current. Compared to what? Compared to your logic transistors. So what I have essentially done is plotted for you the on-off characteristics of your N FinFET and P FinFET in the 14 nanometer Intel technology, the FinFET technology. And you see that the off-state current, if you see the off-state current, is around 10 to the power of minus 3 microamps, which is roughly 1 nanoamp. Now, in 14 nanometer FinFET, the off current is in the order of hundreds of picoamps or 1 nanoamp. However, what we require as a leak current to maintain the specification of 64 millisecond is roughly 30 femtoamps. And that is why your regular logic FinFET transistor, which is built for performance. Why did you build these transistors? So you have very high on currents also. These may not be suitable for access as access transistors in the DRAM technology node, because in DRAM technology node or DRAM technology access transistor cell has to have very, very low leakage current. How do you do that? You facilitate the low leakage current by having something called a recess channel transistor. So what is this recess channel transistor? In recess channel transistor, you are creating this kind of a trench, and your channel is this kind of the channel is formed by digging a hole and making the gate finger insert between the source and drain electrodes. How does this help? The notable feature of this DRAM access transistor, which is your recess channel, really helps to reduce off-state current. This is because, if you think very intuitively, this is a very good technique to increase the effective channel length. See, the effective channel length is increasing because the current has to go all around. You are increasing the effective channel length without changing the distance between source and drain. So you are maintaining scalability but increasing the effective channel length, and by using a thicker gate oxide, you can ensure that the leakage current is very, very low. Okay. There are several advancements that have been done in the recess channel access transistor. In the 90 nanometer node, we just discussed the U-shaped recess helps in reducing or suppressing the off-state leakage. In the 45 nanometer technology node, you started using the saddle FinFET structure, which gives you much better immunity to short channel effect and therefore lower leakage current. Furthermore, in the 32 nanometer channel node, the buried gate oxide structure was introduced just to reduce the coupling between the word line, which is in the gate of the access transistor, and the storage node capacitor, because the gate is buried underneath the silicon's surface. And further, more advancements are also happening in in form of vertical gate transistors to further improve the performance of scaled recessed channel transistors. Okay. The last thing that we want to discuss today is the scaling innovations when it comes to reducing interconnect delay. Remember, DRAM was the first off-chip memory, and the major issue here was the interconnects, the size and the length of the interconnects was creating significant issues in signal integrity, speed, and power consumption. So the first technique in order to remedy this is this technique called embedded DRAM, EDRAM or embedded DRAM. What is the concept of embedded DRAM? In embedded DRAM, what we essentially do is we try to integrate the DRAM process in the same technology or the same processes as your advanced logic nodes. Okay, how is this done? You essentially make the fabrication process of your storage node capacitor compatible with your logic processors. Why are you wanting to do this? It is very simple. The last level of cache, remember from our discussion, the last level of cache is a shared cache between all the different cores of the CPU. We need much larger capacity for the last level of cache for better performance of the CPU subsystem. We want to move from hundreds of MB to few GBs, and this is possible with the EDRAM technology because the EDRAM technology takes 30 to 90 F squared in normalized cell area, but the SRAM, if you remember, takes 150 to 300 F squared. So effectively, for the same area that an SRAM cell needs, you will be able to fit close to 3 times or 4 times or 5 times the number of EDRAM cells, therefore improving bit density. So from the perspective of SRAM, it looks very, very promising. But in terms of your regular DRAM perspective, 1T, 1C off chip, it looks not very good because your EDRAM technology is still 30 to 90 F squared. But that, whereas our regular DRAM technology is just 6 F squared. So of course, you are playing the same bottleneck game of latency versus density. In your regular DRAM cell, you have 6 F squared, but because your fabrication process is not compatible with logic processes, you have to have a separate chip. And if you have a separate chip, of course, latency will improve, but density will suffer. So EDRAM is just a compromise or a very intelligent compromise that device technologists have started to make. Okay, this is one way of trying to integrate DRAM technology within the same or within the same logic nodes so that the interconnect delays is significantly reduced. The other advancement is in that of in packaging technology. In packaging technology, there is a very new concept of heterogeneous integration. So what is this concept of heterogeneous integration? Heterogeneous integration is basically the assembly or the advanced packaging of multiple components. Each component, different chips which have been fabricated by completely different processes. You bring them and you integrate them on the same die into the same functional system or the same chip package. How is this facilitated? It is facilitated through the process, through this fabrication process of having transposers plus TSV technology. What is TSV? TSV is this through silicon vias. You see these through silicon vias, these red color through silicon vias. They are these vertical electrical connections that pass through thin down silicon dies which enable very high density interconnections. Okay, and this interposer is basically a common thin down flat substrate which is generally consisting of silicon that provides the platform to route the signals between multiple chips. So these are your multiple chips, chip 1, chip 2, and you have your interposer technology, interposer layer on which these different chips sit, and through silicon vias are what connect these chips with each other. Okay, so our heterogeneous integration, the first generation of heterogeneous integration was very successful, and AMD already has a product called high bandwidth memory. I suggest you go and read more about it. So this heterogeneous integration in 2.5D ensures or places multiple chips side by side on a common interposer, thus enabling very high bandwidth connections without doing vertical stacking. Now, this simplifies a lot of the fabrication processing and also thermal management. However, what is most promising or more promising is your second and third generation of three-dimensional heterogeneous integration. Instead of stacking them side by side, what you do is you stack them vertically using technology, which even more advanced technology such as bumps and through silicon vias. This offers even shorter interconnects and higher interconnect density. So a small homework I want to give you is that although there have not been any products which have been out in the market from the 3D heterogeneous integration, please go and read about very successful case study of 2.5D heterogeneous integration where DRAM chips have been integrated on the same wafer or the same package as your processor subsystem through this technology called HBM or high bandwidth memory. This is a technology which is patented by AMD. Okay, so with this, we do a very comprehensive study of your DRAM cell, DRAM subsystem architecture, the modes of operation, and also the scaling challenges and the solutions towards going to better and better DRAM technology. With this, we will conclude our fourth module on DRAM main memory technology, and next we will go ahead in our next class start looking at storage, which is NAND flash. Thank you very much. See you in the next class.